Okay, so in the last video we were talking about how to solve problems involving projectile motion, and this is our first example. So in this example we have a stunt driver that's going to drive a motorcycle off of a 50-meter high cliff, and the initial velocity is entirely horizontal, so he's not going up a ramp, just straight off a cliff horizontally, and is going to land on the ground below 90 meters away from the base of the vertical cliff. We're going to ignore air resistance. We need to know how fast he needs to be going in order to achieve this. So again, I always recommend drawing a diagram. So that's what we have here. We've got our cliff that's 50 meters tall. We want to land 90 meters away. We're going to drive off of the cliff with some as yet unknown horizontal velocity. The initial vertical velocity is 0, so all of the velocity initially is in the horizontal direction, and then the bike is going to start to accelerate in the downward direction due to gravity. Keep in mind that the horizontal velocity is not going to change. Whatever this initial velocity is here, it's going to be the same when he lands, because we are ignoring air resistance. So what we need to do is establish what we know and what we don't know. So we know the initial y position. So let's just make a note of this stuff. What is known? We know the initial y position. We know the final y position. We could set this up to be 50 and the final to be 0, or 50 and 0, or we could set the initial position to be 0 and the final to be negative 50. Either way, it'll work out as long as we stay true to our rules that we set up in the beginning. I prefer to avoid dealing with negatives, so I'm going to say the initial position is 50 meters up, and the final position is at 0. What else do we know? We know the initial x position is, we'll call that 0, and the final x position is 90.0, because he's going to end up 90 meters away from where he starts. We know that the initial y velocity is 0. Final y velocity, we don't know. Just before he hits the ground, how fast will he be traveling in the downward direction, we don't know. What is the initial x velocity going to be? No, it's not 0. It's unknown. We don't know that. Oh, that's where I meant to put the 0. Initial x velocity. Unknown. Final x velocity. Again, is unknown, but we do know that these two things are going to be equal to each other because it doesn't change. And we know that g, gravity, is 9.80 meters per second squared. So we take what we know and what we want to know. What we want to know is this initial x velocity. We want to know how fast does the motorcycle need to be going in order to land 90 meters away from the base of the cliff. That's what we're looking for. So a complaint I often get from students is that although they're given all of these formulas, I give you a formula sheet that you can use, it's difficult to know which formula it is that they're supposed to use. So here we have summarized what I wrote out on the previous slide, what is known and what is unknown. So time is another thing that was unknown. I didn't write down. Okay, but all this other stuff is known. if we look at the formulas that are given to you, what I've done here is I've highlighted in yellow all the things that we know. We know the initial, we know the final x position, we know the initial x position. We know the initial velocity in the y direction, we know what gravity is. We know the final y position, we know the initial y position. We know the initial velocity in the y direction, we know gravity, and so on. So what we need to do is to look at these formulas, and looking based on what we know, we want to choose a formula in which we know everything but one variable. So for instance, this first equation right here, if we were to consider using this one first, this would not be a great choice because we don't know the velocity in the y direction, the final velocity in the y direction, and we don't know how much time the motorcycle spends in the air. Two unknowns we can't solve for. We have time in this one. Time is the only unknown. That could potentially be useful. And in fact, time is kind of critical because time is what links these two x and y categories of equations. That's the one thing they each have in common is time. So if we want to eventually get over here to know what the x velocity is, or the initial x velocity, how fast he needs to take off, in order to get there, we need to know time. So this might be the way to go right here. Now this equation we could use this equation to solve for the final velocity in the y direction, but that's not really going to help us out. That's not really ultimately what we're looking for here. Ultimately what we want to know is this, and in order to know this we need to know time, and so I think we need to start off with this equation right here. So it's sort of a process of elimination. Look at the variables that are given to you, determine what it is you need to find out, and then based on those variables, choose the appropriate equation. Okay, so I'm going to write out that equation. Y equals y naught plus v y naught t minus 1/2 gt squared. So the final y position, I'm going to call that 0. The initial y position, 50 meters up in the air. And again, we could set this final as -50 and the original is 0, but I like to avoid negative numbers if I can. So we'll call the initial position 0, the final position 0, the initial position 50. Plus, what is our initial velocity in the y direction? It's 0. Initially, he's not moving up or down. The motorcycle is just traveling horizontally before it goes off the cliff. So that's 0 t minus 1/2. Gravity is 9.80 meters per second squared times t squared. So since this is 0, that term just goes away. Okay, I'm going to move all of this term over to the other side of the equation by adding it. Right now it's negative, so I'm going to add that term to both sides. So I end up with 1/2 times 9.80 meters per second squared times time squared equals 50.0 meters. All right, to get time by itself, I need to take my 50.0 meters and divide it by 1/2 9.80 meters per second squared. And don't forget this. In order to get rid of the square here, we have to take the square root. So we're taking the square root of all this. All right, I'm going to plug that into a calculator and see what I get. Okay, I got 3.19 seconds is how long this motorcyclist is going to be in the air. So that's t, and once we know t, we can use that then to calculate what his initial velocity needs to be. Now, a quick word here over here. This is kind of a lot going on to try to punch into a calculator all at once. And that's another real common mistake I see students making is just simply calculator mistakes. Not putting in parentheses where they need to be. Not following the correct order of operations, or forgetting to square something, or forgetting to take a square root of something. So if you need to, break it down into individual steps. Find 1/2 times 9.8 first, and then take 50 divided by that answer and write that down, and then take the square root of it. You don't have to put it all into the calculator all at once. So just be mindful of that and watch out for the silly calculator mistakes. So we have found t. We know t now is 3.19 seconds. So I can highlight t, highlight the t, the t there, the t there. So that is now included in what we know. So we could find the final y velocity if we wanted to, although we weren't asked to. What we want to know is how fast does the motorcycle need to take off horizontally, v sub x naught. So this equation, we know everything but that. So this is going to be the equation we're going to want to use in order to find what that velocity needs to be. So final x position was 90 meters away from the base of the cliff, equals the initial x position, call that 0, plus vx naught, the initial x velocity, times our time of 3.19 seconds. So solve for vx naught, and that is equal to 90.0 meters divided by 3.19 seconds. Let's put that into the calculator. And I am getting 28.2 meters per second. So that's how fast the motorcycle needs to be going in order to land 90 meters away. And just in case you're curious, that works out to be about 63 miles per hour. So that's how fast the motorcycle needs to go. So you can see we used two different equations. We had to use this one in order to get time, and then plug it into this one in order to find the initial velocity. So this is pretty typical of these types of problems. Get that out of the way. So we have to use multiple equations in combination with each other in order to arrive at the final solution. The next part of the presentation is another example problem, and since I don't want to get cut off in the middle of an example problem, I'm going to finish this video here, and we will start the next example with the next video.